Hi, welcome back to the series. I am Shurov, MSc in Photogrammetry and Geoinformatics with practical experience in GIS, remote sensing, and geospatial data analysis. Let's start the video. GIS represents the world mainly through two data models, Vector and Raster. Vector describes identifiable features using points, lines, and polygons. Raster divides an area into cells containing values. Neither model is universally better, and most real GIS and remote sensing projects combine both. In vector data, coordinates form geometries, and each geometry can link to a descriptive record. A road may be a line with a name and speed limit. A parcel may be a polygon with an owner and area. In raster data, location is defined by the grid, and every cell stores a value, such as elevation, reflectance, or land cover class. A useful rule is that vector suits discrete entities and raster suits values that cover an area. But this is not absolute. Land cover is categorical yet is commonly stored as a raster, while elevation contours are vectors representing a continuous surface. Detail in vector data depends on source scale and vertices. Raster detail depends heavily on cell size and source resolution. File format and data model are related, but they are not the same thing. GeoPackage is an open container that can hold vector features and raster tiles. GeoJSON is a web-oriented vector exchange format. GeoTIFF stores georeferenced rasters, while a cloud-optimized GeoTIFF is arranged for efficient partial web access. Shapefile remains common, but its legacy field and size restrictions matter. Vector is central to cadastral utility, transport, and asset management systems because individual objects and relationships matter. Raster dominates satellite imagery, elevation, environmental modeling, and other cell-based calculations. The models often meet in one operation. A vector field, catchment, or district is used to clip a raster or summarize its pixel values. Raster storage grows with the number of cells, bands, and bytes per value. Halving the cell dimensions produces roughly 4 times as many cells over the same area. Vector storage instead grows with feature count, vertex detail, and attribute volume. Large rasters benefit from tiling, compression, and overviews. Large vector layers benefit from spatial indexes and scale-appropriate geometry. Here is a vector country layer from natural Earth. Selecting a polygon highlights its corresponding attribute record. Filtering the continent field changes which features are shown without converting the layer into an image. When we zoom in, the boundary is redrawn from coordinates and vertices, although its real accuracy remains limited by the source scale. This world cover layer is a categorical raster at 10-meter resolution. Zooming in reveals the cell structure, and the Identify tool reports the class stored in a selected cell. The map may look like an image, but the analytical content is the cell value. Notice that class boundaries step along the grid rather than following infinitely precise lines. Rasterizing this polygon requires an output cell size, extent, alignment, and value. A coarser grid stores fewer cells but shifts and simplifies the apparent boundary. When that raster is polygonized, the new geometry follows connected cells. It does not reconstruct the original line. Misaligned grids can also trigger hidden resampling, so conversions must be documented and validated. Practical rule is simple. Start with vector when individual objects, boundaries, or networks matter. Start with raster when a value is defined across the whole area. In most projects, keep both models and convert only for a specific analytical reason. Always preserve the CRS, scale or resolution, no data rules, and metadata. If this video helped you, please like, comment, and subscribe. Thank you.